Alright, so today we're going to talk about exponential functions and then logarithms and how they relate to each other. And the key part of an exponential function, it's a function where the dependent variable, the x variable, is an exponent. So the key thing is that it happens in our exponent, which is different than anything we've seen before. So we have some restrictions that a is not equal to 0, because then the whole thing would equal 0. B is greater than 0, so we're not looking at negative numbers here. And b is not equal to 1. Because 1 to any power is going to just be 1, and so we would just get a constant function there. And so we're going to look at this, and values of b less than 0 are tricky in that we would have things fluctuating in terms of our powers, in terms of positives and negatives. So b is a positive number. Alright, so if we were to given the exponential equation at the bottom here, where I have 2 times 1.5, that's my base, raised to the x power, I plug in values to figure out what I have going on. So I plug in 1.5 to the negative 2, I flip it over as my reciprocal, I get 0.8, I plot that point, I plug in negative 1, I plot that point, plug in 0, and remember 1.5, anything to the 0 power is 1, that gives me a 2, plot that point, and then I put in 1, I get 3, we can see kind of the shape that's happening here, I get 4.5, and my last one, I get 6.75 as I go through it. So we see we get this kind of nice curve that's happening as we plot our points, which is the exponential curve as we're going through it. We see we don't have a common difference, right? I have plus a half, plus 0.7, plus 1, plus 1.5, plus 2.25. It's growing what we call exponentially. It's growing by an increasing quantity every time. Now the multiple is the same. I'm multiplying by 1.5 to get it each time, but the addition is growing exponentially. So we see our curve there. All right. We have a horizontal asymptote for y equals 0. I can't ever get a negative number out. Now if I have b is greater than 0, a positive value, there's no power that I can raise a positive number to and get a negative out. Unless a was negative, but that would just flip the whole thing over. So I approach y equals 0 as x goes to negative infinity in this case. So I never quite get there, but I'm approaching that asymptote as we come through here. Alright, if I was to graph another one, right, I plug through my points, I get 12, I get 6, I get 3, 1.5, and I get 3/4 and 3/8. I'm just plugging through points. Now this is exponential decay. We can see as x is getting bigger, right, we're getting smaller numbers because my b value is less than a 1. So each time I'm multiplying by a half. If we were to plot these points, we'd get that exponential growth curve mirrored over the y-axis. Alright, so my y-intercept, I plug in x is 0, and I'm going to get out 3. The asymptote is still y equals 0 as x goes to negative infinity, and I plot my points, and there's my exponential decay curve. Alright, we can also use this information to figure out points. If we're given 2 points that we know it passes through, and we're given that it's exponential, we can solve for the equation. So I take the general exponential, and I plug in my points 0, 3, 0 for x, 3 for y, and I find that 3 is a, because b to the 0 power is 1. Plug in the other point, we know what we know for a, and I get 2 is 1 over b, or b is 1/2. So my general form is 3 to the 1/2, 3 times 1/2 to the x power. Same idea for the other 2 points, plug in your values for x and y, solve for a and b, and then you get your general exponential function. So we get y is negative 18 times 3 to the x power. Alright, now there's different ways to do these, but some of them are going to be easy, some are going to be harder when we have to look at logarithms. But if we're trying to figure out what x is, so somehow getting the variable out of the exponent, we hope and pray that we have the same base. So for like the first one, it's 5 to the x power, we can write 25 as 5 squared. That means that x is 2. So that's pretty simple. The next one, we try to write the 1 over 27 as 3 to a power. Well, that's 1 over 3 to the third, which is 3 to the negative third, so x has to be negative 3. For the next one, we'll look at powers of 2. So I express everything as a power of 2, and I solve that 2x plus 4 is greater than negative 3x plus 4. I solve for x, and I get x is greater than or equal to 0. So those are kind of special cases. We're going to move into more specific ones as we deal with things that aren't the same base, and how do we deal with getting those exponents out at that point. Alright, that's where our idea of logarithms come in. So the first question is, what are they? Well, if I was to take x and have a times b to the x power, that's my exponential. And it gives me some value f of x. Well, if I want to turn it around, if I want the inverse, that's where this thing called logarithms come into play. So if I look at it, let's take an example where it's 3 times 10 to the x power, and if x is 2, we get 300. Well, now I want to take that 300 and turn it back into 2. I want to find the inverse. Well, our method for that, right, is I take x and y, I switch them, and I solve for y, because the inverse takes the ordered pair xy and switches it to be yx. So there's my exponential. I switch x and y, and I solve for y. So I get to this point where I get x over 3 equals 10 to the y power, and now I'm kind of stuck. I don't know how to get the exponent out of there. How do I deal with that y up there? So we define something called a logarithm. Log base b of a equals c. Now, key thing, this is not log base b times a. Right? It's log is a function. It's asking a specific question, and that question is, c is the power that I raise b to and get a. Alright? So I'm asking for a power. C is a power. It's an exponent. Well, if I look at what we have, I have y is the power I raise 10 to, and I get x over 3. So log base 10 of x over 3 equals y. That's my inverse. If I look back, sorry, I didn't want to go so far yet. If I look back, I can see that if I took a log base 10 of both sides, I would be given an expression of this, right? This would show up right here, and then I'd have log base 10 of 10 to the y. Those cancel each other, and I'm left with just y. So that's where this piece comes from here. We'll get a lot of practice with it. I know it looks confusing now, but it'll make sense down the road. Key thing to remember is we have this expression, this sentence, this question that we're dealing with when we see a logarithm. Alright. So again, this is the sentence of different variables where x is the power I raise b to, and I get y. That's what log base b of y equals x means. So if I look at the first one down here, log base 2 of 2 to the 4th has to equal 4, right? Because this is asking 4 is the power I raise 2 to, and I get 2 to the 4th power. Well, it's obvious because I have a 4 there. I have 2 to a power, so that has to be the same as that. If I look at the next one, so if I was to write out the sentence, 4 is the power I raise 2 to, and get 2 to the 4th power. Log base 5 of 5 to the 3rd, all right, is log base 5 of 125, which equals 3. We're going to start looking at something called a power law, where I can bring that exponent down in front. And log base 5 of 5 to the 1st, well, that's going to equal 1. 1 is the power I raise 5 to and get 5 raised to the 1st power. Right? We could have looked at it over here too and rewritten this as 125 is 5 to the 3rd, and we would get 3 is the power I raise 5 to and get 5 to the 3rd power. Alright? Again, that will look at one of our properties next time in terms of what logarithms, what they follow. Alright, so let's do a bunch of them real quick. This, if we read it, it looks confusing, but this is asking for, it's asking for a power. And it's saying, what power do I raise 3 to and get 3 raised to the 5th power? Well, it should be pretty obvious that is 5. Right? This one is saying, what power do I raise 10 to and get 10 to the negative 2? The next one is what power do I raise 2 to and get 2 to the 6th power? And then the last one is what power do I raise 4 to and get 4 to the negative 2? Well, now that we've written them this way as powers of 3, 10, 2, and 4, it's pretty obvious. This one is 5, that one's negative 2, that one's 6, and that one's negative 2. Alright? We can solve these as well to figure out exponentials. So if I take the one down here, log base 4 of x equals 0. So this is asking for 0 is the power I raise 4 to and get x. So 4 to the 0 power is x, and 4 to the 0 is 1. So x is 1. Look at the next one. This says c is the power. I raise 9 to, and I get 3. Right? 9 is my base. That's what I get. This is my power. If I write it out, 9 to the c equals 3. That's 3 squared to the c equals 3 to the first. Now it's something simple. 2c is 1, c is 1/2, or the square root of 9 equals 3. So you can see how we can go back and forth between our expression for logarithms and our knowledge of exponents to solve these equations.